Right, today we're going to do 7-7 L'Hopital's rule. Hopefully this is review for you guys. I know you did it in calculus last year. L'Hopital's rules can be used to evaluate limits that are in indeterminate form. What is indeterminate form? If you do direct substitution and you get a 0 over 0 or an infinity over infinity, then that is indeterminate, and you can use L'Hopital's rule. Now, what is L'Hopital's rule? Well, L'Hopital's rule says that if a limit as x approaches c of f of x divided by g of x, if I substitute in and I get a 0 over 0 or infinity over infinity, then I can use L'Hopital's rule. L'Hopital's rule says you can take the derivative of the top and bottom. When I do L'Hopital's rule, I'm going to probably do an equal with an L above it, so you know that I know that they're not exactly the same step, but by L'Hopital's rule, it's legal to do. So the limit as x approaches c of the top derivative divided by the bottom derivative. And that should give me something hopefully I can evaluate. If not, I may have to do L'Hopital's rule again. Now, I'll caution you, don't try to do L'Hopital's rule unless it is indeterminate. If it is a regular one that's not indeterminate, you're not going to get the right answer with L'Hopital's rule. So it has to be indeterminate. One more thing I'll tell you, there are some other forms that are indeterminate, but they all can be written 0, 0, or infinity over infinity. We're going to see them a little bit later in this lecture. Well, let's just jump in and look at some examples. Example 1 out of your book says the limit as x approaches 0 of e to the 2x minus 1 over x. Let's verify that it is indeed indeterminate first. If I evaluate this at 0, I get e to the 2 times 0 minus 1 over 0. Well, e to the 0 is 1. 1 minus 1 over 0 is 0 over 0. It's indeterminate, so therefore I can use L'Hopital's rule. So L'Hopital's rule says take the derivative. And when I take the derivative, I get the limit as x approaches 0 of 2e to the 2x. The derivative of minus 1 is 0 over the derivative of x is 1. Don't try to do a quotient rule here. It's just the derivative of the top divided by the derivative of the bottom. Now I can evaluate by direct substitution. 2 times e to the 2 times 0. E to the 0 is simply 1, so we get the limit is 2. And we use L'Hopital's rule to evaluate it. Let's look at example 2. I'm going to look at a limit as it approaches infinity now. The limit as x approaches infinity of natural log of x over x. Well, if I try to do it by direct substitution, I get natural log infinity over infinity. Well, we know the natural log graph goes off to infinity, so this is indeed infinity over infinity. It's indeterminate. I can use L'Hopital's rule. So by L'Hopital's rule, the limit as x approaches infinity, the derivative of natural log of x is 1 over x, over the derivative of x is 1. So I get, when I do it by direct substitution, I get 1 over infinity. 1 over a very large number is obviously heading towards 0. So that limit would be 0. Let's look at example 3. Let's look at what happens when we approach negative infinity. Now I'm approaching negative infinity. And I'm going to try x squared over e to the negative x. Let's see if it's indeterminate first. If I put a negative infinity on top, I get infinity. If I put a negative infinity on bottom, a negative, and if I put negative infinity there and negative infinity is going towards infinity, obviously you know that e to the x is heading off to infinity. So this is infinity over infinity. It is indeterminate. So I can use L'Hopital's rule to evaluate this. The limit as x approaches negative infinity of 2x over negative e to the negative x. If I try direct substitution, I get infinity on top and negative infinity on bottom. That is indeterminate, so I'm not done. But I can do L'Hopital's rule one more time. The limit as x approaches negative infinity of 2 over e to the negative x. Its derivative is negative e to the x, so those negatives cancel out. Now when I put infinity in, I get 2 over, or negative infinity, I get e to the negative infinity, or e to the infinity, or 2 over infinity, which is indeed approaching 0. And I've used L'Hopital's rule twice to evaluate it. All right, well, that's pretty straightforward. I want you to refer to page 533, and it has the fact that there are really some other indeterminate forms we could look at. 0 times infinity, 1 to the infinity, infinity to the 0, and 0 to the 0. And that discussion's pretty good there to show you that you do need to look at these separately. Now, let's just jump in and look at some examples. Example 4. If I have e to the limit as x approaches infinity of e to the negative x times square root of x. Well, if I put infinity in here, I really end up with e to the negative infinity is going to 0, and the square root of infinity is going to infinity. So it's really a 0 times infinity. That is indeterminate. It's not technically a L'Hopital's indeterminate, so we want to make it look like a L'Hopital's indeterminate. So this could be rewritten as square root of x over e to the x, putting that negative on bottom, which is now when I evaluated infinity over infinity, which now says you can indeed use L'Hopital's rule. So by L'Hopital's rule, this limit as x approaches infinity, the derivative of square root of x is 1 over 2 square roots of x, and the derivative of e to the x is simply e to the x. Well, that is 1 over 2 e to the x square roots of x, which is 1 over infinity, which we've seen several times is heading to 0. All right, this is kind of an interesting problem, example 5. We have the limit as x approaches infinity of 1 plus 1 over x raised to the x. You may or may not recognize this, but we're going to define something with calculus here that you guys actually start learning in Algebra 2, and you'll see at the end what I'm talking about. Well, what is this? I have 1 plus 1 over infinity. If I substitute it in this, it'd be 1 plus 1 over infinity raised to the infinity. Well, this is heading to 0, so 1 plus 0 is 1. So this is 1 to infinity. It's one of those additional indeterminate forms, but we got to make it look like L'Hopital indeterminate before we can go on. So one trick I'm going to use is I'm going to say let y equals the limit as x approaches, infinity of 1 plus 1 over x to the x. And you might recognize this by techniques we did to be able to take derivatives of power to a power. I'm going to take the natural log of both sides, and I can evaluate that limit on the outside. So I'm going to just put the natural log on the inside. So what I end up with is the natural log of y is equal to the limit as x approaches infinity of, now think about the power rule on a log. That x can become a multiplier. X natural log of 1 plus 1 over x now. Well, that's still not quite L'Hopital's rule, but I'm going to manipulate it a little bit to make it look like it. Multiplying by any number is the same as dividing by the reciprocal. So this could be written as natural log of 1 plus 1 over x. Instead of showing multiplication by x, that's the same as dividing by 1 over x. Multiplying by any number is the same as dividing by the reciprocal. So now if I plug in infinity, once again on top I get natural log of 1 plus 1 over infinity. 1 over infinity is going to 0, so this is natural log of 1 on top, which is going to 0. On bottom, I get 1 over infinity, which is going to 0. And finally, it looks like L'Hopital's rule. I think I'm going to need a little bit more space on this one. All right. So now, by L'Hopital's rule, I'm going to say that that's the equivalent of the limit as x approaches infinity of, now we got kind of a messy one to take the derivative of, but it's possible. So starting off with taking the derivative of this one on top here. That derivative is 1 over whatever's inside, 1 plus 1 over x, times the derivative of what's inside, which is negative 1 over x squared. All that over. Now we're going to take the derivative of what's on bottom, negative 1 over x squared. Fortunately for us, those two cancel out. And it leaves me with the natural log of y of the limit as x is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. And if I put infinity in there, I get 1 over 1 plus 1 over infinity, or simply 1. We're not quite done, because we really, if you look back up, we're looking for what y was, not natural log of y, but what I have is natural log of y. So I have the natural log of y is equal to 1. Exponentiate both sides, I get y is equal to e. And what did you just prove to me? You proved me, because y was the limit as x approaches infinity, of 1 plus 1 over x raised to the x. Finally, we have a definition of e using L'Hopital's rule. And that is something you actually looked at in Algebra 2 starting, and you've used e quite a bit since then. All right, let's look at the next example. We'll look at example 6. So the limit as x approaches 0 from a positive side of sine x to the x. If I substitute straight in, I get 0 to the 0. It's one of the quasi indeterminate forms, but we got to make it look like a L'Hopital indeterminate. So I can't jump in to do L'Hopital's rule yet. I'm going to manipulate this a little bit. Once again, I'm going to say let y equals this, and I'm going to take the natural log of both sides. So if I take the natural log of this side, I also have to take the natural log of this side. Makes this natural log of y is equal to the limit as x approaches 0 from the positive side of, using that little trick here, x natural log sine x. The natural log of y is equal to limit as x approaches 0 from the positive side. And we're going to do that same trick. Natural log of sine x over 1 over x. Now the natural log of 0 is approaching negative infinity, and if I put a 0 in here, that's approaching infinity, so that is indeed indeterminate. So now I can use L'Hopital's rule. So the natural log of y by L'Hopital's rule is the same as the limit as x approaches 0 from a positive side. The derivative of sine, the natural log of sine, is simply 1 over sine times its derivative, which is cosine. And the derivative of 1 over x squared is negative 1 over x squared. In other words, that's the cotangent of x over negative 1 over x squared. Rewriting that, I can put this negative 1 over x squared can come to the top as negative x squared. Cotangent goes to the bottom as tangent x. And the reason I want to do that, now if I evaluate this at 0, I get 0 over 0. And finally, I have something that is in L'Hopital's rule. So starting from this function here, using L'Hopital's rule, again, we know that the derivative of that is negative 2x, and the derivative of the bottom one is secant squared x. Now, and I forgot, that's the limit as x approaches 0 on the positive side. Now if I put 0 in there, I get 0 over. The secant of 0 is actually 1, and 0 divided by 1 is 0, and I finally get an answer. All right, one last one. Actually, I think that's going to be enough to get you guys going. All right, I'll be back in a little bit if you guys need help. Thank you.